calcium ions. Now there are some receptors which are in the cytoplasm itself, not the membrane but inside the cytoplasm or the nucleus. And the examples are thyroid hormones. So these are in the cytoplasm or nucleus. The examples are the steroid hormones and thyroid. So if we take the steroid ones, they are lipid soluble. They can dissolve there and they can enter in and they can diffuse through the plasma. So it's a simple way to do it. And these are the example like testosterone. This is the example of a steroid hormone. Testosterone causes structural proteins in the muscle fibers because it makes the structural protein. It increases the muscle size. So these are the steroid hormones. They can diffuse. So this is the plasma membrane. They can get in. If they are in the cytoplasm, they can be attached to the receptor and then they can enter to the nucleus or they are directly going to the nucleus. But these ones, these hormones, what they do, they actually bind to the receptors and then they activate the gene and then this activation goes to the cytoplasm and then the protein structure changes or protein synthesis or protein breakdown can happen and then they can target the cells which are important for this hormone. So this is an example of thyroid hormone. So this is thyroid hormone structure. It is in the receptor, for example, and then it works on the DNA here. So this is inside the nucleus. So here they can again bind to the receptor, they activate the gene, then this protein synthesis happens and they can target cells of interest. So what they do, they bind to the mitochondria, receptors on the mitochondria. So these are the examples of thyroid hormones. So now we will take one by one the endocrine organs. So number one is hypothalamus. And this is very high level of endocrine function because this is the starting point. And they integrate both nervous and endocrine system because it's a part of brain. It is a thermostat of the body and then it also is involved with the endocrine function, means releasing a lot of hormones. So these mechanisms which are involved with the hypothalamus, they could be either hormone secretion or regulatory hormone secretion, means they regulate the secretion of other hormones. So number one, they secrete themselves some hormone. Number two is they regulate for the secretion of other hormones and they contain autonomic centers. And autonomic centers, we'll talk about it. So when they have to secrete itself, the hormones, so these hormones basically are released by the hypothalamic neurons. And there are two hormones, they are transported and released by posterior pituitary. So the only two hormones are released from hypothalamic neurons, and these are ADH. ADH is synthesized by, so hypothalamus, as you must have done in ANP1, they have a lot of nucleus or nuclei in plural. So they have a lot of different kinds of different types of nuclei. What are the nuclei? Supraoptic nuclei. You don't have to go into detail, but you need to know these names of the optic nuclei, so because ADH is released by this nucleus of the hypothalamus. Then they release oxytocin, which is synthesized by paraventricular nucleus. So this is another nucleus. Paraventricular means they're surrounding the ventricles. So now you can see over here, so this area, pink one, is the hypothalamus. So this one here, these are the neurons. So these green ones are the neurons, which are hypothalamic neurons. They release ADH and oxytocin. And also there are, this is in the next few slides, hypothalamus is regulating some other hormones to be released. So these are secreting regulatory hormones. And the third one is autonomic center within the hypothalamus. one, the green, for example, this is the anterior lobe of pituitary gland, this is the posterior lobe of pituitary gland. So this one, for example, the purple one, they are released by anterior lobe of the pituitary, which secretes multiple hormones. And we will talk about this. While this green one, which are from the hypothalamic neurons, so these bulgings are basically the part of the neuron, and these ones, they release ADH and oxytocin in the circulation. The third kind is autonomic within the hypothalamus, so they regulate the adrenal gland, and they release epinephrine and norepinephrine. So this is about now regulatory neurons, which are here in the purple. So these regulatory hormones, they control anterior pituitary endocrine cells. So these cells are controlled by these regulatory hormones, which are located in the hypothalamus. So there are two kinds of regulatory hormones, releasing hormone or inhibiting hormone. Whenever something is needed, so they will release RH or releasing hormone, and when the job is done for that hormone, they will release inhibiting hormone so that the hormone release could stop. Then third one is autonomic centers in the hypothalamus, and these ones we are talking about, these pink ones. So they are allowing the hypothalamic hormone to reach the thyroid cell in the anterior pituitary directly without mixing and diluting in the general circulation. So they don't get into the general circulation, and before that they reach the target cell. So here you can see, so this is part of the hypothalamus, this is the paraventricular nucleus, this green one, these are the neurons, and they go and they release oxytocin and ADH, and then these are the blood vessels. So this is actually artery, and these are the veins, and here also, because the hormone, whatever is released, it has to go to the blood circulation. So now, for example, this one, the blue one here, so they are controlled by these, and these cells will be releasing them, and they will put these hormones into the circulation. Same way here, they put them into circulation. There is a hypophyseal portal system, and this means they have the network of the blood capillaries, arteries, and the veins, and these are called portal vessels, and these are secondary capillary network. So pituitary gland itself, so hypothalamus, we are done with that. Now we have pituitary gland, it is also known as hypophysis. This is a small, very round, oval gland. This is actually sitting, have you heard of sala turcica, the sphenoid bone? In the skeletal system, you guys did it in AG1. So this is the sphenoid bone, has a structure called sala turcica. So they are lying inside sala turcica. There are two lobes of pituitary gland. Anterior is also known as adenohypophysis. Pituitary gland itself is called hypophysis. So the anterior one is called adenohypophysis, and you need to know these synonyms. Posterior lobe is called neurohypophysis because it is connected to the hypothalamus by this area, which is called infundibulum, and the area which connects to that infundibulum, this is called as medial eminence. Pituitary gland releases 9 hormones. And as I mentioned, they have anterior lobe and posterior lobe. Total, within these two lobes, they release 9 hormones. Out of those, 7 out of 9 hormones are released from anterior or adenohypophysis. And these are called tropic hormones. Trope means they turn on, basically. Turning on means they start the reaction. So these are turning on hormones because they turn on the other endocrine gland. So if something has to happen to the adrenal gland, so they turn on those. So therefore they are called tropic. and 2 out of 9 are released from posterior lobe of the pituitary, which is called neurohypophysis. And all these 9 of them, they are binding to the membrane receptors and they use cyclic AMP as the second messenger. So that means, are these lipid soluble or are these water soluble? If they are using second messenger, are they water soluble or they are lipid soluble? Come on, guys. Second messenger are used only when they cannot go through the plasma membrane. Why they cannot go through the plasma membrane? Because they are water soluble. The second kind, which is lipid soluble, they can go directly because they can be dissolved there. So these are all, these hormones are basically water soluble hormones, and they use a second messenger called cyclic AMP. So now you can see this is the posterior lobe of the pituitary, this is the anterior lobe of the pituitary. And then this is basically, this is the structure they are talking about. This is called median eminence. And this part is called infundibulum. So now we'll talk about 9 hormones of the posterior or of the pituitary gland. Out of those 9, 7 of them are from anterior lobe. And these are, and I have given the full names later slides. So TSH, ACTH, and gonadotropin, which are 2 of them, follicular stimulating hormone and luteinizing hormone, growth hormone, PRL, and MSH. All these are 7 hormones. So kind of a question I can give you, I give you some of these and then I add into that which are not anterior lobe hormone, and you should be able to basically pick up which ones are not anterior or which are posterior. So first one is TSH. So now where it is released from and what does it do? So TSH, and what does it do means they are targeting the thyroid gland. As the name suggests, they target the thyroid gland, and what do? They stimulate the release of thyroid hormone. So basically, our targeting thyroid glands means thyroid gland should release thyroid hormones, and it is released in response to thyrotropin releasing hormone or TRH from hypothalamus. So I talked about hypothalamus has either releasing hormone or inhibiting hormone. So now this is TRH means thyrotropin releasing hormone. So they will be released in response to the thyrotropin releasing hormone. So there are a couple of things you need to know for every single hormone. They are targeting thyroid gland, and thyroid gland basically is stimulating the release of thyroid hormone. And when they are released, when you have the response from thyrotropin releasing hormone. So first, hypothalamus will release TRH, then it will target the thyroid hormones, which will basically are coming from thyroid. Other one is adrenocorticotropin hormones, or it is known as ACTH, and then I can ask a question if I can give you adrenocorticotropin and gonadotropin, for example, and what is their abbreviation and what is their full name. So those kinds of questions can be asked. This hormone, ACTH, is also known as corticotropin, and it stimulates, so where it is targeting, it stimulates the release of steroid hormone from adrenal cortex. So they are targeting adrenal gland, not only adrenal gland, but the cortex part of the adrenal gland. And why they are released? In response to what? So they are corticotropin releasing hormone again. Like it was thyrotropin releasing, here it is corticotropin releasing hormone. So these names are basically coming from this. Gonadotropins, they regulate activity of the gonads, which are testes in the males and ovaries in the females. And they are released in response to gonadotropin releasing hormone. Okay, are you getting the point? There are releasing hormone first. So these hormones from the hypothalamus, when it is released, then they will activate gonads. For example, testes and ovaries. These are two gonadotropin, FSH and LH. And in full name, FSH is follicle stimulating hormone, and it promotes ovarian follicle development. And it stimulates the hormone called estrogen. FSH in male, so FSH is actually both in male and female. In the males, it promotes maturation of the sperm, and in FSH is inhibited by inhibin. So whenever there is no need of this hormone, then it can be inhibin which can control that. Luteinizing hormone in females. So they induce ovulation, and you will be doing this in the development actually chapter. And luteinizing hormone promotes secretion of estrogen and progesterone, and these hormones actually prepare the body for possible pregnancy. LH in males, it stimulates interstitial cells of the testes, and you are not done with the interstitial cells because they will be in the, when we do the reproductive system, the testes anatomy, you will learn about interstitial cells. So in the male, the testes interstitial cell, they are the one they produce sex hormone called androgen, and first it produces the testosterone. So in males, they produce basically androgens or testosterone. So this is a little bit now more like kind of memorized. What are these hormones? You have to memorize what they are doing. The next hormone is called GH. G means growth hormones. So they stimulate cell growth and reproduction by accelerating the rate of protein synthesis. When the baby is born, then it basically develops, it becomes the infant becomes the, the child, which is adolescent. So basically what happened, the growth of the person goes because of the rate of protein synthesis goes up. And this hormone is regulated by hypothalamic hormones. Again, they are growth hormone releasing hormone and growth hormone inhibiting hormone. When somebody is totally mature, so then this hormone is not, basically it is inhibited. The action of all these growth hormone, this one is basically their receptors are on the cells in body, including skeletal muscles, and the response is uptake of amino acids. So I don't think you need to go through this, but you need to know. Okay, how these growth hormones can act on different tissues. So in epithelial and connective tissue, have you done this epithelial and connective tissue? We have different kind of tissue, epithelial tissue, connective tissue, and muscular and you did ANT1.
Skeletal.
Huh?
Skeletal.
Scout. So they are acting on the epithelial and connective tissues, and they also work on adipose. Adipose means fat. So they work on fat cells. So they stimulate breakdown of triglyceride, which release fatty acid into the blood. There is a phenomenon called glucose sparing effect. So tissue usually use fatty acid instead of glucose to generate ATP. And that is how they are sparing the glucose. They're not using the glucose, but they are using basically fatty acids, and that effect is called glucose sparing effect. Then we have PRL, which is called prolactin. Prolactin means pro means before, lactin means basically coming from milk ejection. So they work with other hormones to stimulate memory development. During the pregnancy and nursing time, This stimulates milk production by mammary glands. Melanocyte stimulating hormones, it's called MSH. So these melanocytes, where they are found? You did integumentary system, right? Integumentary system is the skin, right? So melanocytes, they are in the skin, so they stimulate the melanocytes of the skin to increase melanin production. So now this one summarizes all of these hormones, which are 1, 2, 3, 4, 5, 6, 7. From which gland? Pituitary gland. Which lobe of the pituitary gland? Anterior. So now this will be summarizing. So we have, this is thyroid, right, gland. This is adrenal gland. This is ovary. This is testis. These are skeletal muscles. And this is mammary gland. And this will be the skin. So thyroid stimulating hormone is acting on thyroid gland. Adrenocorticotropic hormone is basically acting on adrenal gland. Follicle stimulating hormone is involved with the ovary, maturation of the follicle. Luteinizing hormone, so they are in both male and female, and here it's shown the testis. This also goes for the lactation. Growth hormone, they go for musculoskeletal system. Prolactin, it helps in mammary gland development, and MSH or melanocyte stimulating hormone is actually acting on the skin melons. Now, hormones of the pituitary gland, so there are only 2 of them, ADH or anti-diabetic hormone and oxytocin. So ADH is also known as vasopressin. And again, you need to know this synonym. It is released, why? Because in response to different things, and these are those. When there is an increase in solute concentration of the blood, so osmoreceptor. Osmo means osmolarity, sensing receptor. So when there is an increase in the solutes, so then this hormone is released, and whenever there is a decrease in blood pressure or blood volume, that also it will be released. And what it does, it acts on the kidney to retain water and decrease urination, so that you don't lose blood. Oxytocin, this is by the name, it's called swift birth, so it's oxytocin, as you know, this is involved with the muscle contraction in the wall of the uterus, which actually produces labor and delivery. And it basically is stimulating the contraction of myoepithelial cells in the mammary gland too, which promote the ejection of the milk. So basically it's doing both the things for labor and delivery and also ejection of the milk. So these are 2 of those, and it says uterus, for example, it releases oxytocin. It's basically it's acting on uterus, which controls the labor and delivery. So just somehow this is misplaced. This ADH is related to the kidney because it can basically inhibit the urine formation so that the urine is not very diluted. Yes.
So I know in the last slide it said that it has unknown functions in sexual activity. Is that why they sometimes recommend having sex in order to induce labor? Because they know that it increases in oxytocin.
So oxytocin basically it works for labor and delivery in a feedback, positive feedback loop. So hypothalamus is releasing it, for example, and it goes to the myoepithelial cells, which are muscle cells of the uterus. And then they start releasing, and then it goes back, and then again they release more oxytocin, and again it goes back. So it's called positive feedback. And the positive feedback is the one which actually produces labor and delivery. Otherwise, the mothers cannot deliver the baby. So oxytocin works that way, yes.
Okay.
So there is a negative feedback, so the control of hormone secretion is called negative feedback. Means some hormone is needed to control the homeostasis of the body. That's called negative feedback. Means they negate the change. Negative means negation, so they negate the change in anything in the body. And positive feedback is they increase that actually. So these things are opposite to each other. So this is for example, I have given an example, you don't have to worry about it, this is a white slide. So you have a control mechanism, like you have thermostat at home, for example. So negative feedback means it doesn't change it. Outside the temperature is 98, for example. But if you set up your thermostat at 72, it does not want to change it. So it negates the change. So that is that, and that thermostat, which is the heating system in your thing, if you set up at 70 degrees, so then whenever it goes more than 70, this will turn on the temperature, and then whenever it goes down to 70, so it depends on what you have fixed for. So then it will go back. So that's kind of negative and positive feedback in the sense that it negates the change. So that's all I was talking. But in human life, this is about your thermostat at home. So for example, blood sugar rises. It goes up, receptors in the body sense the change. That your sugar is more, so then control center in the body for sugar is pancreas. So the pancreas release insulin into the blood, which basically decrease the blood sugar. So this is negation, that body controls on its own. But then there are some diseases in which they cannot do it. The body cannot do anything because either the receptors are wrong, or pancreas is not producing that insulin, or insulin is not attaching to the receptor. Those are other things, but this is the way the body works for the glucose. So now this is summarizing. For example, this is hypothalamus. So these are releasing hormones. So they release anterior lobe, one hormone is released, and it goes to the endocrine organ like thyroid or adrenal gland or pancreas or gonads. And then second hormone is released, and the target cell actually is affected. And these are summary of these releasing hormones, and these are the hormones from pituitary. These are the organs, so TRH or thyrotropin releasing hormone, they work on the thyroid stimulating hormone, and it is thyroid gland, and these are called thyroid. So negative feedback, in some instances, both releasing and inhibiting hormones are part of the regulatory process. So if they need releasing hormone, they will release releasing. If they need to inhibit that, then they will release inhibiting hormone. And the example is prolactin inhibit the release of PRF, which is prolactin releasing hormone. And one time it is inhibiting, the other time it can stimulate the releasing of prolactin inhibiting hormone. So they can go together. Either they can release or they can inhibit. So this is an example of stimulation. From the red one, they are stimulating, and this way they are inhibiting. So this growth hormone, inhibiting hormone is inhibiting, means two lines are for blocking, and the arrow is for stimulating. So this is again, you have this inhibiting, and these are releasing hormones. And that summarizes the whole pituitary gland, 1, 2, 3, 4, 5, 6, 7 of anterior pituitary and 2 of those. And then how they are connecting the whole body. So this one is connecting to the adrenal gland, they release this. This connecting to the thyroid gland, they release thyroid hormone, then this. So this summarizes whatever I said in the few slides. So now how these hormones, they interact, they communicate with each other. So this we will talk about thyroid gland. what it produces and the function of these hormones. Then we go through parathyroid, then we will go through the adrenal, then we will go to the pancreas, then pineal gland, and then what can go wrong. So this is part of the clinical knowledge. Thyroid gland, gross anatomy, you know where it is. So this is the trachea, for example. So this is located on the anterior surface of the trachea and inferior to the thyroid cartilage. Isthmus, so it has two lobes, and those two lobes are connected by isthmus. And some of you have seen this thyroid gland in the models, and some of you will see it today. So you can see, so this is thyroid cartilage, and this one is thyroid gland. This has one lobe, right and left, and they are connected by isthmus. And this is trachea. Histology you mean like, you know, how, if you take a slice, how the cells look like. So histology, thyroid gland has a lot of follicles. And in the slide, some of you have seen the follicular cells, the colloid, parafollicular cell, and some of you will see today. So the follicle, basically, they have follicular cells. These are surrounded by hollow spheres. So there is, and I'll show you a picture. So this is a hollow sphere, which is called as colloid, and it is surrounded by these cells. These cells are follicular cells. So every colloid is surrounded by follicular cells. So this one is surrounded by this one is surrounded by this one is surrounded by this. So all of them are surrounded, and in between those follicular cells, these are called parafollicular or C cells. So if you see this colloid, so the follicles are spheres, like hollow spheres, there is nothing in there. They are followed by simple cuboidal epithelium. And in P1, you must have done that epithelial cells, these are different kinds, simple and striated, right? Striated means multiple layers, simple means one layer. And either simple or striated, they have different shapes. Squamous, cuboidal means cube shape. So this is surrounded by simple cuboidal epithelium, and the cavity holds the colloid protein. It's called colloid because it has a protein. And how this protein is made is called thyroglobulin. Thyro means it's coming from thyroid. So these follicle cells which surround the thyroid, this follicle or colloid, they secrete a protein called thyroglobulin and secrete into this colloid. So that's why they're called thyroglobulin. Then there are some other kind of cells called parafollicular cells. This is also called as C. C means clear. They are between the membranes of follicular cell, and they are very specific to release a hormone called calcitonin. And what calcitonin does, it actually regulates calcium ion concentration in the body. So this is about that. Thyroid hormone production, and you don't need to go into detail, but these are the names of these hormones actually. So there are 7 steps, but so thyroid hormones are thyroxine, which is called T4. And why it is called T4? Because it has 4 iodine, and T3. So they have thyroxine with 4 iodine molecules, and trioiodothyronine means 3 molecules with iodine atoms, and thyroglobin molecule which contains 4 to 8 molecules of T3 or T4. So these are the hormones of the thyroid. Usually 75% of T4, these molecules, they travel in the blood, which are attached to the proteins called as thyroid binding globulins. Globulins are always protein. So that's why these 2 things only from this region. And they are showing about here the thyroglobulin, which is inside the globulin, inside the colloid, and this protein is formed. And then after that, when this hormone is released, they have iodine molecule T4 and T3, and then they go to this is the blood vessel, and whenever it is released, it goes to the blood vessel. Parathyroid gland. So this is thyroid, this is isthmus, where they are connecting the lobe. Parathyroid gland, they are embedded into the thyroid glands. So these are two pairs, one on each side, these purple ones. They are embedded in the posterior side of the thyroid gland. Parathyroid gland, they have two cells. One is called occipital cell and parathyroid cell. Occipital cell, they know that they are different than this, but they don't know what do they do with it. There is nothing known about that. Parathyroid are the main or the chief cells of the parathyroid gland, and they produce parathyroid hormone, which is easy to remember. Parathyroid hormone, what it does, it regulates the calcium level in the blood. So this is basically parathyroid gland slice, and they have these blood vessels here. These are the thyroid follicle, as we talked about. This is the colloid, this is the follicular cell, this is another follicular cell. But these are surrounding the follicles are peptides. So these are the chief cells, these are occipital cells, their function is not known. How do they basically control calcium? Homeostasis means they don't want to change anything with the body's metabolic things. So parathyroid and calcitonin. These are two hormones from thyroid glands. They have opposing effects. So if one goes up, one goes down. So in healthy people, PTH in combination with calcitriol is the regulating the calcium concentration. And if people remove the thyroid gland, has no effect on calcium. So they show these pictures. So for example, the body has normal blood calcium level. Now, this is disturbed over here, and how it is disturbed, it's basically decrease the blood calcium level. So now this parathyroid gland, they will release parathyroid hormone, and this hormone does all these three things, and then homeostasis is restored. On the contrary, if it is more calcium level, then thyroid gland again will produce calcitonin. So instead of PTH, they will produce calcitonin, and then again they will regulate the calcium, and homeostasis is recovered. Next gland is adrenal gland. Adrenal gland is also known as suprarenal. Supra means it's on the top of, renal means kidney, right? So it is sitting on the top of kidney, and it sits on there, and this is basically retroperitoneal. And again, I will ask you, what is retroperitoneal? You guys must have done it. So retroperitoneal means they're behind the peritoneal cavity. So you have done the dissection of, what dissection you guys did? The fetal pigs, right? Red? Red. It's same thing. So when you open the body, so kidney, you cannot see the kidney, right? Why? Because your digestive system is ahead of it. So that digestive system in the cavity, which is called peritoneal cavity. So it is behind the peritoneal cavity, and when you remove the digestive system, like alimentary canal, like ileum, large intestine, small intestine, then you can see that. So there are some organs in the body which are called retroperitoneal. One of them is reproductive system, then bladder, and kidney. They are all retroperitoneal. So this is called retroperitoneal, means behind the peritoneal cavity. Adrenal gland has this structure. It is surrounded by structure called capsule. Then it has inside superficial part is called cortex, inside part is called medulla. So adrenal cortex is the outer part and corticosteroids. So outer part, which is cortex, they release corticosteroids. These are basically 24 to 25 hormones. But luckily you don't have to remember all 25 because they have given the name corticosteroids. And medulla, which is the inner part, and you will be seeing, and some of you have seen the slide of adrenal gland. Medulla is inside part, it produces epinephrine and norepinephrine. So you need to know adrenal cortex produces corticosteroid and medulla produces epinephrine and norepinephrine. So this is the kidney, suprarenal means on the top of the kidney. This is surrounded by the capsule. Then these lines they are showing here, these are cortex, and inside is the medulla. Medulla is actually, when you see in the higher magnification in the scope, you can see there are a lot of blood vessels. So these blood vessels are basically marking the point that it's medulla. Cortex is a couple of layers actually. So now these are the layers. So there are 3 zones of adrenal cortex. Zona means zones. Glomerulosa, fasciculata, and reticularis. For the lab exam, you don't need to worry about these, but I think because there are different hormones, so you have to worry about the test that you need to memorize. Glomerulosa is basically the top layer after the capsule, and it secretes mineralocorticoids, which is basically aldosterone. And this mineralocorticoid, they increase the reabsorption of the sodium and water. And you will do in the kidney, for example, you will see that everything from the filtrate from the kidney is reabsorbed by the body, and that's called reabsorption of sodium and water. Otherwise, everything, whatever is in the filtrate, you will lose it. It basically reclaimed by the body, by the kidney. So this mineralocorticoid will help to that. And when they are released, they stimulate a system called renin-angiotensin aldosterone system, and they are inhibited by hormones which oppose them. So this is all memorization. Fasciculata is the middle part of the cortex. This is the large part of the cortex. They secrete glucocorticoids. So you have to remember, this one, glomerulosa, produce mineralocorticoid. This one will produce glucocorticoids or steroids. Then they secrete zona fasciculata. First they secrete cortisol and corticosterone, and then they go to the liver. Liver converts them into cortisol and cortisol. So these are the prohormones, meaning they are the early release, and these ones by the liver they are converted to these. Then what do these glucocorticoids do? They affect, gluco means glucose, they affect glucose metabolic activities, and cortisol, they have anti-inflammatory effect. When there is an infection, so it affects that. The last layer of the cortex is called zona reticulosa or reticularis, which is actually reticularis means they are basically making the network. They secrete androgens, and androgens, what do? They stimulate development of pubic hairs before puberty. This is the slide of adrenal gland. So as you can see in the beginning, there is a capsule which covers the adrenal gland, and then from here until like here around, this is all cortex. So one layer is glomerulosa, which produces mineralocorticoid, they produce glucocorticoid, and this one will produce this, which is androgens. So this whole thing is cortex, but inside, so if you see the pinkish thing here is the blood vessels. And I have some slide in the lab actually to show you that how do you identify cortex versus medulla. So what does medulla do? It secretes epinephrine and norepinephrine. And what does these hormones do? So they are related to cardiac activity increase, increased blood pressure, increased glycogen breakdown, and blood glucose. So these things all memorization. So this is basically whole summary. Glomerulus or glomerulosa, they produce this, fasciculator produce this, reticulus produce this, and medulla produce this. Then next, endocrine organ is pancreas. Pancreas is both exo and endocrine because it produces the hormone, but also it produces something else than hormones. Therefore, it's called as exocrine also. So the pancreas is again retroperitoneal. So, because it's behind the peritoneal cavity, it is basically this, which is in the form of a loop. There are two parts of pancreas, again exocrine part or endocrine part. Exocrine part, 99% of the pancreas is exocrine, which does not produce hormone. Only 1% of the whole pancreas produces hormones. But exocrine part is called acini, and endocrine part is called as islets. So you need to, if you are given a slide to identify for the lab purposes, you need to identify either the pointer is towards the exocrine part or endocrine part. So acini, they have clusters of the cells, pancreatic acini and attached ducts. While islets, they contain small groups of hormone-producing cells that are scattered in clusters. And therefore it's called islets, or it is also known as islet of Langerhans. So these are the cells from pancreatic islet. There are four types, alpha, beta, delta, and F cells. Alpha cells produce glucagon. Glucagon raises the blood sugar. Beta cells secrete insulin. Insulin lowers the blood glucose. So definitely they are working in opposition to each other, opposite to each. If this one raises the glucose, this one will put it down. Delta cells, they produce peptide hormone, which is actually similar to the growth hormone inhibiting hormone. So this suppresses the release of glucagon and insulin. So why? Because when the job is done, your glucose is controlled, then you need the inhibition of this hormone, because you cannot have hormone release all the time. That will be bad for your body. So now they will have inhibiting hormone. Lastly, the F cell, they produce pancreatic polypeptide or PP, which inhibits gallbladder contraction. This is a picture from the internet. As you can see, this is the surrounding area, which is the islet. And so islet has scattered cells, and these are having compact cells. So all these parts are called acini, and this whole area is called as islet. How does glucose is controlled? That's called glucose homeostasis. So insulin and glucagon, they control the glucose level. Insulin and glucagon, they are opposite in fact. So as blood glucose rises, beta cells, they secrete insulin, and when it goes down, then alpha cells release glucagon. And this is showing again the same way. This is the control, the normal. If it is disturbed, pancreas will produce this. If it goes high, then they will be producing insulin. So here they produce glucagon, here insulin. So this is something I have. It's not having an eye. Try. But it is. Okay, thank you.
You're welcome.
The sugary snack you devour enters your digestive system and is broken down to simple sugars like glucose. Glucose enters the bloodstream, causing an increase in blood glucose levels. But various mechanisms bring blood glucose back down to its normal level, the set point. This is an example of homeostasis, the body's tendency to maintain relatively constant internal conditions. Hormones produced by the pancreas regulate blood glucose levels. Let's zoom in. When blood glucose levels are high, glucose molecules leave the blood and enter beta cells in the pancreas. The beta cells respond by releasing the hormone insulin. Insulin enters the bloodstream and is transported to cells all over the body. Let's see what happens in the liver. Insulin binds to receptors on liver cells. This causes the cells to take in more glucose. Inside the liver cells, glucose is converted to glycogen, a storage molecule. Blood glucose levels decrease as glucose is taken up by liver cells and other body cells. As a result, less and less insulin is released by the pancreas, and blood glucose levels stabilize at their set point. This is an example of how negative feedback maintains homeostasis. What happens if you've skipped lunch and your blood glucose levels are low? Let's zoom into the pancreas again. When blood glucose levels are low, alpha cells in the pancreas release the hormone glucagon. Glucagon enters the bloodstream and acts on target cells in the liver. Glucagon binds to receptors on the liver cells, signaling the liver cells to break glycogen down to glucose. Glucose is released. And blood glucose levels increase. As a result, less glucagon is released by the pancreas, and blood glucose levels stabilize at their set point. In this way, two hormones with opposing effects allow the body to maintain homeostasis of blood glucose levels. In diabetes, the body is unable to maintain homeostasis of blood glucose levels. In type 1 diabetes, the beta cells of the pancreas are destroyed by the immune system, and so no insulin is produced. In type 2 diabetes, the pancreas produces insulin, but target cells do not take up glucose. In both types of diabetes, when blood glucose levels rise, cells do not take up the additional glucose, and so blood glucose remains high. This example shows the importance of homeostasis in everyone's life.
Okay, so next is pineal gland. It's part of epithalamus. So in the brain, you must have some hypothalamus, thalamus, and epithalamus, which is on the opposite side of the pituitary gland. So it contains neurons, glial cells, and some cells which secrete. It's called pinealocyte. And these cells are the secretory cells which produce melatonin from molecules of the serotonin. So this is the brain, and then this is the slice of the brain, and we have in the lab also this model. So this is pituitary gland. And now on the opposite side, which is on the back side, that is pineal gland. And the cells, they produce the hormones called pinealocytes. Melatonin is produced from pineal gland. What does it do? Number one, melatonin inhibiting reproductive functions. So it plays major role in timing of human sexual maturation, and it declines at the time of puberty. Also, it protects against the damage by free radicals. Like, there are some toxins in the body, for example. So it is a very effective antioxidant. And third thing, it is basically setting of the circadian rhythm functions. So it sets daily changes in physiological processes or day and night cycles. So if they give you to identify pineal gland, they can ask you which hormone. So melatonin and hormone, what does it do? It's basically on the day-night or rhythmic cycles. Diabetes mellitus. Mellitus word comes from honey, means sweet. So it can be caused by genetic abnormalities in either you have inadequate insulin production, so the body is not producing insulin enough, or abnormal insulin. So insulin is produced, but it is not attaching. Diabetes mellitus is basically characterized by glucose concentration high enough to overwhelm kidney absorption. So you can have hyperglycemia, means presence of abnormally high blood glucose, or glycosuria, means presence of glucose in the urine, or polyuria, means you have excessive urine production. So these are all the signs of diabetes. There are two types, type 1 and type 2. Type 1, inadequate insulin production. So as I said, this is inadequate insulin production in type 1. And this basically, they receive insulin daily. And type 1 diabetes often develops in children and young adults. So this is actually in like teenage or younger than that, it has been diagnosed in the people. Type 2 is common form of diabetes mellitus because more people have type 2 diabetes than type 1. And what happens in this insulin resistance, so they are producing the insulin, but this patient, they produce normal amount of insulin, but tissues do not respond to this properly. Clinical problems caused by diabetes mellitus. It disrupts metabolic activities throughout the body. Without insulin, or insulin is not working, cells cannot absorb glucose from surrounding, and also causes abnormal changes in the blood vessel structures. Diabetes can cause retinopathy, means retina word comes from the eye, means people can have complete blindness caused by damage of the capillaries in the retina. Diabetic nephropathy, nephron word comes from kidney, so basically degenerative changes in the kidney. Diabetic neuropathy, neuro means the nervous system, so then abnormal blood flow to the nervous system, and also it can cause peripheral tissue damage in the limbs, which is basically, usually it happens in the feet. It can lead to the loss of toes or major portion of the foot. So this is eye, increased heart attack, then diabetic nephropathy means, kidneys are not working, neuropathy, the nervous system, and then this is the last part of this is, I'm going to be going for 10 more minutes. Now we will talk about hormone interaction and how these function, then adaptation, and then clinical function. So there are 4 types of interaction of the hormones. So how they interact with each other. One is from 2 hormones at the same time has 4 possible outcomes. One is called antagonistic, when they go into the opposite roles. Additive means one hormone adds up to the second hormone and it has an additive effect. Permissive means one hormone is needed to add to the second hormone, and then integration means they have integrated effects. Antagonistic means opposing effect. So the result of both antagonistic effect is between hormones into this. So these effects are weaker than those produced by either hormone. So one hormone is producing 5, second one is producing 5. So if it is additive, it will become 10. But here, these antagonistic effects are weaker. And these, so this is the antagonistic. This is one hormone, for example. So it attaches to this. It increases the cellular activity. The other hormone actually decreases the cellular activity. So these are going into the opposite directions. Additive means net results of the interaction of two hormones is greater than acting alone. And that is known as synergistic effect, meaning they are together. So in this case, additive effect results are greater than the sum of individual ones. So for example, 1 is 5, 1 is 5, so it will be somewhere between more than 5 at least. And this is the example of this is glucose sparing effect. So one hormone here, second hormone is here, so then they will increase the activity. Third one is permissive, means one hormone is needed for the second one to react. So this hormone, for example, you have a permission of this hormone and then only this hormone will work. So that's why they are called permissive. An example is epinephrine changes the rate of cellular energy consumption only when thyroid hormone is there. And the last one is integrative effect. So they are complementary to each other. And examples are calcitriol and parathyroid hormones. So this is one hormone which activates the enzyme complex 1. There's another hormone which is basically activated enzyme complex 2. Okay, so now what is the long-term regulation of blood pressure, blood volume, and weight? These are the more important things now, so that whatever you learn into the physiology of the body. So long-term regulation of blood pressure and volume involves pituitary gland, adrenal gland, and endocrine cells from heart and kidney. Remember, these are two organs, for example. Their primary role is not to produce hormones, but the secondary role is to produce hormones. When you have to decrease the blood pressure for controlling the internal environment of the blood pressure, so what happens? The heart wall. So the heart is actually, it has a wall, it responds to overstretching by releasing this hormone. So the heart wall overstretch to release natriuretic peptide. Natri means come from sodium word and uresis means making water. So the effect of this natriuretic peptide is reduction of blood volume and pressure. So you are decreasing the blood pressure by natriuretic peptide. On the contrary, so this is normal, it is disturbed, for example, now the heart wall overstretch, they produce natriuretic peptide and then it does these, and then increase fluid, decrease pressure, all these things happen and then they decrease the fluid. When you have to increase the blood pressure, it will be opposite. So then what happens, endocrine cells in the kidney, they release this enzyme called erythropoietin or EPO, which increase blood cell production, and renin, which activate renin, angiotensin, aldosterone system. So these are two systems, they work to increase the blood pressure. And again, here this is normal, it is disturbed, so you have blood pressure and volume decreased. Then you will have EPO, which is erythropoietin, it will actually increase the blood cell production, and then another one will go for renin, angiotensin, aldosterone system, and then they will restore. Regulation of the growth. So it requires cooperation of many organs. It's not only one. And primary hormones which regulate growth is insulin and all these from parathyroid hormone, calcitriol and calcitonin, thyroid hormones, reproductive hormones and growth. So this is number one, insulin allows the passage of glucose and amino acid around the growing cells. PTH, calcitriol and calcitonin, these three of them, they promote absorption of calcium salts for bone deposition. Calcitonin accelerates the rate of bone deposition so that bones are strong. Thyroid hormone, they are required for nervous system and skeletal system development. Reproductive hormone, they actually affect the osteoblast. These are the cells of the bones at various locations. Androgens in the male and estrogen in the female have different target tissues. In children, the growth hormones support protein synthesis and cellular growth in skeletal and muscular system because they have to grow. And in adults, it assists in energy metabolic activities. So this is in the newborn, you have insulin, parathyroid hormone, thyroid hormones, and reproductive hormones. So for these hormones, there is a phenomenon called stress. How do you get stress? So stress is emotional or physical condition which basically threaten the homeostasis. So it threatens the internal, basically physiology of the body. And what happens when it is too cold? You start shivering, right? So this is one of the examples in response to drop in body temperature. And this is called as GAS, means General Adaptation Syndrome, or stress response. So this is the physical response due to the exposure of stress causing effect, we call as GAS. So what is the stress? So there are three phases of stress: alarm, resistance phase, and exhaustion phase. I'll go through those. Alarm phase is the immediate sympathetic response to stress. And so for example here, this is the alarm phase, it's called fight or flight. So then the human body is actually responding for flight or fight. So what hormone is released during this phase? That's what you need to know. Epinephrine is the dominant hormone for this. Second is resistance phase. So the body tries to resist. So you enter this phase after a few hours of the alarm phase. And in this phase, glucocorticoids are released. And effect of the resistance phase is mobilization of body's energy reserves. So body has energy reserves, so they can be used at that time. So body is trying to resist with the stress. And then lastly, if you can see, for example, here, this is called exhaustion phase. When energy reserve is used and there is no energy reserve left. So what happens, these reserves cannot be maintained, and then people go to the exhaustion phase, and homeostatic regulation breaks down in this phase. Causes of this endocrine disorders. So how these work? Endocrine disorder can be either they are secreted more hormone or it is secreted less hormone. When it is secreted less, that's called hyposecretion. Hypo means less. Or they are secreted more. Both of them are problems. These are the common causes of hyposecretion, that metabolic factors, physical damage, there is a tissue damage, there is an organ damage, or you're born with this disorder. Metabolic factors, deficiency in the substance which is needed to synthesize the hormone, that you don't have that. Example are hypothyroidism, which is basically inadequate iodine in the diet, but it can be controlled so that you can be given the iodine. Physical damage, the damage to the endocrine cells or the target cells. So even the endocrine cells are going okay, but the target cell, they don't get fat because those target cells are wrong. And congenital disorders means you are born with that, so then you are unable to produce normal amount of hormone. So this is summarizing metabolic factors, physical damage, and congenital. This also can be caused by presence of abnormal receptors. So here we talk about that hormone release is not possible, but it is also possible hormone is released, but hormone has to be attached to the receptor. So those receptors are off. So then they are unable to respond to these hormones. And the examples are type 2 diabetes. People have insulin production, but the insulin does not go to the target cell. That is how this response of insulin is nullified. So now these are clinical modules. These are only a few slides. So what happens and why it happened, which endocrine organ is responsible? These are the kind of questions I'm looking for. Acromegaly, this is by the overproduction of growth hormone. And when after epiphyseal plate, have you heard about epiphyseal plate? In the femur, like in the legs, for example, there is a line called epiphyseal line or epiphyseal line. Again, you can say in two ways. Once the child has grown as the puberty time, that this plate is closed. So means the child cannot grow more than that. But if there is an overproduction after it has been fused, then this kind of problems can happen. And the signs are broad facial features and enlarged lower jaw. So now you need to know why acromegaly is happening. Means overproduction of growth. Thyroid gland can cause a lot of problems. So goiter is one of those things which you can see here. So this is basically associated with the thyroid hyposecretion due to the iodine deficiency. This is called infantile hypothyroidism because it happens in the infants only. It's a congenital, means the kids are born with that because you have thyroid hormone deficiency. So infantile hypothyroidism, you can basically say this is a defect of thyroid gland, right? But here goiter, you have to find out why it happened. It is because of the hyposecretion of the iodine. Adrenal gland also can be wrong. So there are two diseases related to the adrenal gland deficiency, Addison disease and Cushing disease. So Addison disease is caused by hyposecretion of corticosteroids and especially glucose. Cushing disease is caused by hyper. So this is hypo. This is hypersecretion of glucocorticoids. And in this case, the people have accumulation of adipose tissue or adipose cells in the cheeks and in the base of the neck.